Okay, so now we'll talk about how the second derivative affects the graph of a function. So concavity. So we're going to have concave up or concave down. So you can pause anytime and write this down. So concave up means the cup faces up if there is a cup. So like this or like this or like what I drew on the graph there. Okay, cup faces up. That's the main idea. So you can think of it as happy face. So happy face is concave up. Okay, more technically, F is concave up on I being an interval, if all tangents lie below the graph of F on the interval I. Okay, concave down is the other way around. Okay, you can think of it as, unhappy face. Cup faces down. And so on. Now we have all tangents are below. Oops, I wrote the wrong thing. Where did I write this? Oops, I wrote the wrong thing, not below. All tangents are above. All tangents are above F on this, interval I. Yeah, remember I is like, AB closed, or could be AB with excluding one, or, all those different combinations. Okay, so that's concavity. So how do we find concavity? Well, it's actually the second derivative that we will use to determine concavity. So we're going to call this the concavity test. And it says that sine of F double prime determines concavity, more or less. Okay, so sine means, is it positive or is it negative? So a positive F double prime is going to give me concave up. A negative F double prime is going to give me concave down. And if F double prime is 0, that means there's no concavity, no, let's say curvature. So you have a straight line. Okay, this is all kind of roughly speaking, but it's a good way to conceptualize it, at least at the beginning. Okay, so let's write this down. So if the second derivative is positive, then we're going to say F is concave up. So CU stands for concave up. If F double prime is less than 0, F is concave down. Oops, CD. Sorry, I'm not being very consistent here. So CU and CD. And before I do an example, one more definition. Okay, for the first derivative, we had something called a critical number. For the second derivative, we're going to have something called a inflection point. So we'll say C, no. So see, this is a bit confusing. We're going to say point. We're going to need an x value and a y value. So the x value is c. Is an inflection point. So the point, x value, y value. This is different than critical number. Critical number was just an x value. Okay, so this is a little bit confusing for some students. It's an inflection point if, f double prime of c is 0 and f is continuous at c. Okay, so f being continuous at c rules out some strange situations like vertical asymptotes. Anyways, we'll get to that. Well, let's do an example. Let's see. Okay, find the intervals of concavity of f of x is equal to 2x cubed minus 9x squared plus 12x minus 3. And also find all inflection points, IP, inflection point. So when I say intervals of concavity, concave up, concave down. So tell me when it's concave up, tell me when it's concave down. And also find all the inflection points, IP. So we want to find f double prime. So we start by finding f prime of x, 6x squared minus 18x plus 12. F double prime of x is 12x minus 18. So if you look at your concavity test, which you just wrote down, I need to find out when is f double prime positive and when is it negative. So I start by asking when is it 0? Well, I get x is equal to 18 over 12, which is what, 3 over 2. And from that, you can form a number line. Put 3 over 2 there. And then you do some test points. Let's say in blue here. F double prime of x is 12x minus 18. F double prime of 0 is negative 18. F double prime of, let's say 2 is 6. So what do we get? Our test point 0 gives me a negative second derivative. So we have concave down here. And then for 2, I got concave up. So now I've realized that I have made a mistake in my definition of an inflection point. So let's go back to the inflection point definition. So please pause the video and return to your inflection point definition. Okay, I want you to cross this out. So what we should be saying is that if concavity changes, and f is continuous at C. Sorry about that. So returning to our example, so we can see at 3/2, concavity does change. Okay, so at 3/2, I go from concave down to concave up. So what this looks like, I'll tell you later, but for now, we go at 3/2, we go from concave down to concave up. So IP, the inflection point is x, x is 3/2, y is equal to f of 3/2, which is a long calculation I do not feel like doing here. I'd be plugging this in, this 3/2 into my function, and which is, what's the next one? Minus 9, 3/2 squared plus 12, 3 equals, you work this out in your calculator, turns out to be 3/2. Okay, so you have to do this. You have to work this out because the inflection point is a point, x value and a y value. So the IP is x is 3/2, and coincidentally, in this case only, or it's just a coincidence that x and y are the same. Okay, let me repeat. IP inflection point is, and I need an x value and a y value.